Welcome back. In the second part of this section, we're going to now introduce a formal definition of the limit. Because, of course, the intuitive idea of x getting as close to c as we'd like and the y values getting closer and closer to some real number, that's a nice way to start. But, of course, we don't want to have to rely on having graphs at a hand to be able to tell if a limit exists. We want to have a nice way to formally recognize whether the limit exists as x approaches some number or not. So what does it actually mean for that limit to exist? So I'm going to talk about the limit, and then as I talk about it, I'm going to start drawing things and doing a little bit of diagramming. So the first thing we have is f is going to be defined on some open interval containing c, not necessarily defined at c. And that's because we said before it doesn't really matter what's happening at c, whether something is happening that agrees with our limit or whether nothing's happening. We don't really care what's happening at c, but the function is defined on the values around c. So we're definitely have some function on the left and some function on the right. So when we say an open interval containing c, C is not one of the endpoints. C is somewhere in the middle, and so there is stuff on the left and there is stuff on the right. So I'm thinking about a function, and I want to talk about this function, f of x, and I want to talk about x approaching c and my limit being L and what that means. So okay, I guess I'm going to have to modify where L is. Should have drawn my graph before I labeled it. That's always good advice, I suppose. Okay. So the first thing that we say is if you want to have a limit as x approaches c of your function being L, then we have to have the following. Number one, L needs to be a real number. So by me plotting this as a point, you can assume that L is some sort of real number, not necessarily positive. C doesn't have to be positive either. This diagram's just for illustration purposes. And then we have these two Greek letters, an epsilon and a delta. We have for any epsilon bigger than 0, there's a delta bigger than 0 such that, and then a bunch of things. So first I'm going to interpret what these refer to. Here, when I have the absolute value of x minus c, I'm talking about the distance between my x values and c. And so what is delta then? Delta is the distance between x and c. So if you went delta units up from c or delta units down from c, all of these values would be in that little interval where x minus c absolute value is less than delta. In other words, we're talking about all those values that are within delta of c. So if you're in that little interval of x values, then your y values will be epsilon away from your limit. So in other words, in this little interval that we've gone at from delta below c to delta above c, all of our y values are guaranteed to be within the limit plus epsilon and the limit minus epsilon. In other words, if you pick any closeness for y values, I can tell you a closeness for x values where if x is close enough to the x value that I said, if you're that far away or less, then the y values will be as close as you'd like. So in other words, no matter how close we want to be to our limit L, we can get there just by getting close enough to C, by just reducing delta, getting smaller and smaller and smaller. So that's formally what we mean by a limit. So if the limit exists, then if you pick epsilon to be any number, then I can find some delta so that if you are within delta of that point C, then your y values will be within your epsilon of L. We're going to do a proof of a limit, and then after we do that proof, we're going to actually use the proof to illustrate something. So before we do, though, Just a couple of things about the proving process. So when you're starting to prove any theorem or any sort of a statement, you begin by assuming the premises that you've got, supposing them to be true. So here, if you go back to what we said for the formal definition, we are supposing that you have any epsilon bigger than 0, and this is what we have to show, that we can find some delta, and so that if you start off knowing that that's true, so that if x minus c is between 0 and delta, then we'll be able to conclude that f of x minus L is less than epsilon, where L is whatever our limit happens to be. So when we do our proof, that's what we're going to start off with. We suppose that epsilon is going to be bigger than 0. We're going to have to then state delta, because that's what we have to show, that if you start off with x minus c being between 0 and delta, that you will get your function is within epsilon of whatever that limit has to be. So delta probably will depend on epsilon. Usually it does. When we do work, when these sorts of proofs, we do our work sort of on the side first, doing some rough work, and then we're going to formally present our proof afterwards. But before I do, though, I'm going to, so first off, introduce the problem. We want to look at the delta epsilon definition of the limit and use that to prove this statement, that the limit as x approaches 2 of 5x plus 2 is 12, which that should not be a big shock to you, because you know that this is the graph of a straight line with a y-intercept 2 and a slope of 5, and definitely the point 212 is on the graph. You definitely, this is not a surprise to anyone. As x is getting close to 2, if you looked at the graph of this, the y values are getting close to 12. So now we want to prove that, though. And so to do that, we're going to have to do the following. We're going to have our proof start off with letting epsilon be bigger than 0. I'll have to say something in this part here about what delta is. That'll be where I'll have to come up with my delta that I have, because now I need to start with, if I have x is close enough to 2, so in other words, if x is between 0 and 2, if the absolute of x minus 2 is between 0 and delta, then a bunch of steps, and hopefully at the very end of it all, we'll be able to conclude that therefore our function minus the limit is less than epsilon. And that would allow us to conclude that the limit as x approaches 2 of our function is 12. This is just me outlining things according to our definition of the formal definition of a limit. That it's, if you have any epsilon bigger than 0, then you'll be able to find some delta where, if x is between where you're looking the limit at is distance no more than delta, then you can conclude your function minus your limit is no more than epsilon. We need to connect these two statements. So this is like the body of an essay. We need to fill that out. And of course, to help fill that out, we'll need to know what delta is. So now we're going to attack the rough work. So again, notice that I can write this out just by knowing what my limit is that I'm trying to show. I will always start with epsilon bigger than 0. I'll always start with if x minus wherever I'm looking for the limit at is less than delta, and I'll always end with function minus the limit value less than epsilon, and that allows me to conclude, therefore, that's my limit. And your job is now to fill in the middle. So let's go do this and do some rough work on the side. And we're going to do that by sort of working backwards with what we need. We need 5x plus 2 minus 12 to be less than epsilon. And of course, that's the same thing as saying that you need 5x minus 10 to be less than epsilon. And you might notice here that 5 factors out. So actually, I could rewrite this as 5 times x minus 2 less than epsilon. So fun fact about absolute values, If you have absolute value of a times b, that's the same thing as absolute value of a times absolute value of b. So for products, you can split up absolute values, not for sums and differences. So if this was a plus, that would no longer be true. That would not be the case. But for multiplication, yes, it certainly is true. So I'm thinking of doing that here. I'm looking here on the 5 times x minus 2 business, and I think, well, I could split that up into absolute value of 5 times absolute value of x minus 2. But of course, absolute value of 5 is the same thing as 5. So I could really say we've got 5 times absolute value of x minus 2. And actually, now I notice something. If I divided by 5, I would say absolute of x minus 2 is less than epsilon divided by 5. Now, the thing is, in my proof, I want to start off with x minus 2 being less than delta. So if delta was epsilon over x minus, if delta was epsilon over 5, then I'd be able to follow the chain of steps to get to my function minus my limit less than epsilon. So, okay, that's my job that I've done here. I've done my ref work to figure out that everything is good, provided that I've got that as my choice for delta. So now I'm going to go back to my proof, and I'm going to say to myself, okay, I can get rid of the bracket now because I'm going to fill it in, and I can say let delta be epsilon over 5. Okay, so now I can fill in the proof to connect the two statements, the if and the therefore. So if 0 is less than absolute of x minus 2 is less than delta, then that means x minus 2 absoluted must be less than epsilon over 5, which means that 5 times absolute of x minus 2 must be less than epsilon, which means that absolute value of 5 times x minus 2 should be less than epsilon, which means that 5x minus 10 is less than epsilon, which gets me to 5x plus 2 minus 12 less than epsilon. And so there we go. We've shown that pick any epsilon you would like, and if I let delta be that, be epsilon divided by 5, then if x is close enough to delta, then my function will be close enough to 12. So therefore my limit as x approaches 2 for my function is 12. Okay, so now let's actually use our proof and just sort of put this into action with what we've shown. So here we've shown in the proof that 5x plus 2, the limit as x approaches 2 is 12. So I might say to myself, okay, well, how close do I need to be to get all of my y values being between 11.95 and 12.05? Or in other words, I want all of my y values to be 12 plus or minus 0.05. So this is how far I need to be away from my y values. If you're remembering from your proof how close you need to be in the y direction, that was epsilon. So in other words, what we've just said here is that in the little example that I've got coming up, that epsilon is 0.05. So in other words, I'm asking how close to 2 do we need to be to guarantee that all the values of my function are within epsilon being 0.05 of 12. And we want to know how close to 2 do we need to be. In other words, we want to know what is delta. And so we know from our previous proof, we said that delta was just going to be the same thing as epsilon divided by 5. So if I want my y values to be within plus or minus 0.05, then my x values need to be within plus or minus 0.01. So in other words, if my x values are within 0.01 of 2, so if they're between 1.99 and 2.01, then my y values are going to be inside the interval from 11.95 to 12.05. And that's sort of the whole idea of what our proof is showing, that you can pick any amount of closeness you would like, and I can tell you how close you'd need to be in terms of x values. So if you wanted to do this again and say, I want all my y values to be between 12.9995 and 11.9995 and 12.0005, so making epsilon even smaller, well, you'll just choose an even smaller delta. So if we're even closer to 2, then the y values would be even closer to 12.